All right, welcome to another fantastic edition of Pre-Cal Matters. We're in chapter 4, section 1. Remember to like and subscribe. Heck, I don't even care if you like it. Give it a thumbs down. I don't care. Just subscribe. Tell all your family and friends about the awesome math content on this channel. All right, we're recording live in my favorite first period class of the whole year. We call this class first period. Yeah. All right, so if y'all remember COVID from 2020, who doesn't, right? uh, we had people getting sick. Okay, we had people getting sick. So if you look at t equals 0, which might have been the first time the guy ate that bat in Wuhan, uh, we had an initial case of COVID, right? And soon he was like coughing on people and having drinking out of other people's cups, and everything. The disease started to spread at an increasing rate. You could say that it was increasing exponentially. And that would be true, right? The more people that got sick, the more people that got sick. Does that make sense? The more people that were sick, the more people that got sick. It works the exact same way as populations, except instead of procreation, we're talking about just getting other people sick. All right, now, it gets to a point, or it got to a point, where it could not continue to increase at an increasing rate. The reason being is because we have this upper horizontal asymptote in addition to the horizontal asymptote at y equals 0. This one is called y equals L, where L is called your carrying capacity, and it's your limit to growth. It's your limit to growth. So what this number might be depends upon the situation. If we're talking about the spread of COVID, y equals L might be the world population. Okay, what is the world population? It's what, 7 point something billion, right? As there are more and more people that are infected, there are fewer and fewer people that are not infected. Would you agree? It's easy. So the disease cannot continue to spread at the same rate that it started because there's not enough people to infect at the same rate. It's like, hey, I'm going to infect you now. Like, nope, I'm already infected, dude. Darn it. Now, it's still going to increase. It's still going to increase, but it's going to increase at a decreasing rate. It's going to change its curvature right there. We call this point right here the inflection value. It's where the curvature changes. It goes from increasing at an increasing rate to increasing at a decreasing rate. Or in here, we could say the graph goes from concave up. That's how we measure we measure curvature with concavity. We say concave up to concave down. The graph changes its curvature, which means it's changing its concavity. It goes from being part of a smile in blue, concave up like a cup, to part of a frown in green, concave down like a frown. Okay? Now, where that inflection value occurs is very, very important. We don't know where it occurs on the t-axis just yet. We don't know when it's growing at the fastest rate. That's another important aspect of the inflection value. It's where the disease is spreading at the fastest rate. We do know where it happens on the y-axis, though. It always happens at y equals L halves. So whatever your carrying capacity is, exactly when half of the population is infected, that's when it's growing at the fastest rate. That's when the number of people that are infected equal the number of people that are not infected. Before that, there's more people that haven't been infected, so it continues to increase at an increasing rate. After the halfway point, population-wise, there are fewer people that haven't been infected, so it can't continue to spread at the same rate. It still increases, but at a decreasing rate. Okay, let's say something else about the inflection value. It's where it changes from concave up to concave down. It's where the curvature changes, and it's where the graph is increasing at the fastest rate. Now, if you look at the blue graph would start like this. It would start looking like an exponential growth. It would come from the horizontal asymptote, and it would increase at an increasing rate. The thing is we typically don't use the exponential growth model to the left of t equals 0. So we're not going to see the horizontal asymptote on the left. Usually we start at t equals 0, and from there it represents exponential growth. Okay, so this is modified exponential growth. And it's how most things that do experience exponential growth in the short term, it's how most of them experience growth in the long term. They can't continue to grow at an increasing rate. Imagine if the COVID continued to increase at an increasing rate. What would this curve continue to do? It would go up to where? Infinity. Well, if we're measuring population on the y-axis, is it possible for the population to equal infinity? Not at all. Okay? So you can't have infinite populations. And that's why they experience a short term exponential growth like this. And then at the halfway point of the population, they curve the other way and they approach the upper horizontal asymptote. All right, we call this type of growth, we call this logistic. Logistic growth. It's a soft G sound, not logistic. Logistic. Logistic or logistic, however you want to say it. Logistic. We pronounce it like logistic. Logistic growth. Okay, there's the phonetic spelling. Now, lots of things grow logistically, like the COVID disease, right? But what else grows logistically? Rumors. Rumors. Okay, so let's look at example 11. A horrible rumor, a dastardly rumor begins to spread on the New Braunfels High School campus. Let's assume for the sake of this that the population is not 200. I need to add another zero there. Let's assume the population is 2,000. Okay? So I need to put a zero there on my notes. I mean to every year and I keep forgetting. Let's say the population is 2,000. That's going to be my limit to growth. You can't have more than 2,000 people hearing about the rumor on campus when there's only 2,000 people on campus. Agreed? Okay, now look at this. Carlos, Petunia, and Wallace. These three people are the ones that begin telling people the dastardly rumor. What is the dastardly rumor? That titanium necklaces really do not increase energy, nor do they increase your balance. I don't know if you remember several years ago, but titanium infused necklaces were all the rage. You probably wore them in elementary school. Professional baseball players wore 3 or 4 at a time. And you could go to Dick's Sporting Goods and you could buy one for the sum of 60 something dollars for a titanium infused necklace. And if you were walking in the mall, if you actually went to a mall, those kiosks in the middle of the walkway, they would be selling them, and they would have demonstrations where a guy would be all lethargic and nearly falling over, and then he put on a titanium necklace, and he would start jumping up and clicking his heels. He was full of energy, and then the guy working the booth would try to push him over, and he wouldn't fall over, and they'd be like, "Whoa, that titanium necklace is giving him energy, and it's increasing his balance. Give me 2 of them." And they were selling like hotcakes. Brady, you say you still have yours? Do you ever wear them?
No,
Not since elementary school. Okay. Well, back when these things were selling like hotcakes, Carlos, Petunia, and Wallace, these three people on campus, began spreading the rumor. Okay, the rumor spreads according to this logistic equation. There's the equation of the logistics. This is what it looks like. Now, notice it has a very characteristic look. It has 2,000 in the top, which is your L value. This is your L. That's your limit to growth. It's always going to be in the numerator. And then you have 1 plus or minus a number times E, which is 2.7, remember, to the tth power. We're using T instead of X. And we're measuring R of T to be the number of people who have heard the rumor. So instead of Y and X, we're using R of T, the number of people who have heard the rumor, as a function of time T. So you can see the exponential piece in the bottom, can't you? You have the numeric base E and the variable exponent T, but you have the limit to growth in the top. All right. It says how many people on campus originally heard the rumor? Carlos, Petunia, and Wallace told some people at T equals 0, and we want to know how many people that was. So here's the first thing you do. You go to Y equals. If your calculator ever freezes, just reload it. Go to Y equals, and let's type it in. Hit alpha X. Alpha X gives you the horizontal division bar. We'll type in 2,000 in the top, and then 1 plus 115E. E is the second feature on the natural log key. So if you hit second ln, which is to the left of the 4, you get e to the power of negative 0.97, and then we use x instead of t. If you click to the right a couple of times, you can see what your equation looks like. You compare it to the one that is given, and except for the x and the y instead of t and the r of t, if it looks the same, you're good. All right, now don't hit graph. Now you go to your window. What are we measuring on the x-axis? We're measuring time. What is a good lower bound for our time? Where should we start? 0. I'm going to start at 0. What is a good number of days, which is what we're measuring it in, to let go? You want 10 days to go by? Or you want a week to go by? 2 weeks to go by? Let's go 3 weeks. That would be how many days? So this is what you play with. You just reason it through. You can always come back and adjust this. We're going to give it 3 weeks for the rumor to spread. Now, your Y-min is easy. We have a horizontal asymptote at 0. I'm going to go negative 100. That gives me a little bit of buffer. Here's why I want a little bit of a buffer. Your calculator uses the top of the screen and the bottom of the screen to write information. What should my upper horizontal asymptote be at? 2,000. Let's go 2,100. Let's give it a buffer of 100 above 2,000. So I'm doing a buffer of 100 below and 100 above. You can even do 1,000 below and 1,000 above if you want. Whatever. I just did 100. And then you can leave everything else the same. Hit graph. You should see an S curve. Do you see an S curve? The logistic curve is sometimes described as an S curve. If you don't see the S curve, you have either typed it in wrong or you're in the wrong window. Do not begin answering the questions unless you see the S curve, okay? All right, how many people originally heard the rumor? Round to the nearest whole person. So here's what we're going to say. On part A, we have to indicate our method. So I'm going to say R of 0. That's what I'm going to show. This is a good free response question on the test, by the way. R of 0, that would earn a check. That's like saying at the ordered pair colon. Okay. Now I'm going to go to the home screen. I'm going to get out of there, and I'm going to recall my equation. Alpha trace number 1 of 0. Boom. And I get 17. It says to round to the nearest whole person, so you just want to put 17. Or you can put 17.241 and then the squiggle sign, which is approximately 17 people. So you're going to get a second check for the 17, and you're going to be eligible for a check by having the units on there, people. So there was a group of 17 at t equals 0 that heard about it. This could be like the number of people subscribing to Corpy's World on YouTube, by the way, right? You tell some people, and then they tell other people, so on and so forth. All right, that takes care of answer A, question A. How many people originally heard round to the nearest whole person? All right, to the nearest whole person again. Find the number of people who have heard the rumor after 1 day, 2 days, and 5 days. So I'm going to do R of 1 day, R of 2 days, and R of 5 days. I'm on my home screen again, so here I go. Alpha trace number 1, open parentheses, of 1. It's 44.84. So if you want to just put 44 people, that would be fine. That would be your fourth check right there. In other words, you don't have to write down 3 decimals and then put the squiggles.
Would you always round down?
Well, so yeah, because the 45th person hasn't really heard yet, right? Completely. Now, I would also accept 45. If you put 44 or 45, I would accept both of them. But what I'm saying is if you want to round to the nearest whole person directly off your calculator, that's fine too. You don't have to put the 3 decimals and then the squiggle. If you do put the 3 decimals and then the rounded answer, you do need to make sure you have the squiggles in between, not an equal sign, because you'll lose points then. All right, then we'll do the same thing. Alpha trace number 1 of 2, and we get 114 people. That would be your 5th check. And then after day 5, alpha trace number 1 of 5. So we're just accessing the equation, 1,052 people. So you can see it's growing pretty quickly here. Already on day 5, more than half the student body knows about this rumor that titanium necklaces don't work. They do work if you're trying to look fashionable. They were a fashion trend. All right, part C. How many people have heard the rumor when the rumor is growing the fastest? How many people have heard the rumor when the rumor is growing the fastest? Very good. What special point do we give to that point where it's growing the fastest? L divided by 2. It's the inflection point. Yeah, it's the inflection point. It's where it's growing the fastest. So you don't have to show any work for that. All you have to do is just say 1,000 people. And as long as you have units on there, you'll get your next check, which is your 7th check. How many people have heard the rumor when it's growing the fastest? Now, it says on what day did that occur? So now I need to say R of T equals 1,000, and that'll be your 8th check. And I can't do this one from the home screen because I'm not given the input, I'm given the output. I'm trying to find the input. The way that I find the input when I'm given the output is by finding the point of intersection. So now I got to go to Y2, and I have to graph 1,000. And you'll see it intersects right there. Where the 2 cross, that's your inflection value. How do we find points of intersection on the calculator? Second trace number what? 5. And then we go first curve, enter. Second curve, enter. Guess, enter. We just hit enter, enter, enter. And then we get T equals 4.891. We'll do 3 decimals here because it didn't say to round to the nearest day. So on what day? It happened on day 4.891. So we were done with the 4th day, and we were 89 hundredths into day 5. Okay, and that will be days. So if you want to answer the question, this is actually on day what? On day 5. Yeah, it happened on day 5. Yes. Oh, I graphed 1,000 in Y2. When you're given the output, when you're given the Y value and you're trying to find the X value, you can't do it from the home screen. The home screen only works when you're given the input, you can find the output. If you're given the output, you need to graph it in Y2 and find the point of intersection, second trace number 5, enter, enter, enter. Now notice the notation here. This would be your 9th check right here. I have R of T equals 1,000, and underneath there I have T equals 4.89. Make sense? R of T equals 1,000. You can even add these words here if it helps you. When T equals 4.891 days. If that'll help you with the notation, that's fine. All right, and then the last part. Describe the end behavior. What does this mean in terms of the rumor? So on part D, how do I describe the end behavior? What notation do I use to describe end behavior? The limit. So the limit as T goes to infinity of R of T. That's the notation that would give you the 10th check. And then all you got to do is evaluate it. What's happening? It's approaching 2,000. Yeah, you can even verify it on the calculator. Alpha trace number 1, you can plug in 100. After 100, oh, we've already teased the calculator. The calculator thinks it actually equaled 2,000. Is that correct? Did your calculator just lie to you? Your calculator just freaking lied to you. Stupid calculator. Maybe it's Minnesota lying to us. Maybe this is their way to try and make New Braunfels High School dumber. We know the answer will never equal 2,000, but it's so close to 2,000 that your calculator gets a rollover error and it just rounds up to 2,000. So we know that the limit is equal to 2,000 people. Okay, now what does this mean in terms of the model? So in theory, the number of people who have heard the rumor only approaches 2,000, the entire student body. In actuality, do you think everyone on campus will eventually hear in actuality? Because in theory, the entire campus, if you wait a billion years, no one will, that last person still doesn't know fully. What? What is it about titanium necklaces? The equation of the equation of the equation? What? But in actuality, it will likely reach all students at some point. So, are these mathematical models perfect for predicting 100% of the time? No, they have a relevant domain over which they are pretty accurate at predicting. But that's all they're used for predicting, for extrapolating outside the data. The further you go outside the data, the less likely it's going to be correct. That's why when you see those hurricane models, there's like 9 or 10 different paths it can take. As you go further and further out, those paths tend to diverge. But if you go closer and closer to where the hurricane actually is, they're pretty much all right on top of each other, right? It's a lot easier to predict in the short term than it is to predict in the long term because there's limitations in the long term. All right, that's it. That's how you do that type of problem. The situation may change, but the way you use the calculator is the same. You write your notation down. If you're given inputs, you do it from the home screen. If you're given the output, you graph it and you find the point of intersection. And then you know the end behavior is the upper limit to growth, and then it's growing the fastest at the inflection point, which is at half that point, half the y value in the numerator. That's it. Any questions on logistic growth? By the way, there is logistic decay if you're interested. Logistic decay. I'll just say this since we have a little bit of time. Logistic decay looks like this. It starts here and it goes like this, and then it cools like this. If you've ever heard of Newton's law of cooling, Newton's law of cooling is logistic decay. You have a cup of coffee and you just set it out in the room. It's going to lose temperature very rapidly in the beginning because the temperature differential is greater. But as it gets closer and closer to room temperature, it can't continue to lose heat at the same amount because there's less heat to lose. So that's an application of logistic decay. All right, clear your calculator so the next person has a clean bowl when they start. All right, and I'll post this one on the YouTube channel, and it'll be the first video from 2023 from y'all's class. Way to go, first period. Give yourselves a round of applause. All right, nice.